Everyone, so this is going to be your lecture on section 8.1, which is sequences. So these notes are going to have a couple slides that we're just going to skip over, and you're welcome to look at if you have extra time and want to play around with these sequences a little bit more. I'll put up those resources if you want to dive in a little bit deeper, but I'll make it very clear what you need from this section to move on to the other sections, and what is just interesting stuff that we're not going to need that you can dig into, go down the rabbit hole if you want to, but it's completely not necessary. So in this video, we're just going to go over the things that are necessary to learn about sequences that we're going to use in the future. So let's start off. The first thing that we need to do is define a sequence. So as you can see here, a sequence is just an ordered list of numbers. And so the way we're going to, in general, write this is something like A1, A2, A3, A4, and then dot, 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 dot. So for example, maybe you have a sequence that looks like 1, 2, 3, 4, and you go, you go, you go. So we're going to be dealing with infinite sequences, so this set of numbers just keeps going forever and ever and ever. And then one way we're going to deal with these, which is really nice, is to think of them as a function. So the one that I've just written down isn't too bad. So a function from the natural numbers to whatever you want. So we'll say the real numbers, because these numbers in our sequence do not have to be nice whole numbers like this. They can be anything we want them to be. So for example, this sequence that I just wrote down right here would be the function that takes in any natural number n and just sends it to itself, n. So I could write that as a sub n is equal to n. A sub 1 is 1, a sub 2 is 2, a sub 3 is 3, so on and so forth. So that's a pretty simple one. We could get a little bit crazier. I could do something like 2, 4, 6, 8, dot, dot, dot. So in this case, well, you can hopefully see the pattern, and what you might want to do is get a formula for this. So a sub n is equal to what? Well, if we take a little time to think about this, we could say, well, 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8. And so what we're looking for is just what's the pattern here. And hopefully it's not too bad to see. I just take my n, that's this left-hand side, n, and then I double it. So there's my formula. So we're going to be doing a little bit of this practice, and we're going to need this a little bit later, being able to say, here's a sequence of numbers. Can I turn that from just this list of numbers into something that has a form like this? So this is a closed form. Oops. So can I take a sequence of numbers and turn it into just a formula? Because the formula is going to be really nice to work with, which we'll see why in just a second. One thing to add into this is I'm starting at 1. Each of these was A1, A2, A3, A4, and so on. You don't have to do that. If you have any coding experience, you probably aren't used to doing this. You probably start things at 0. So you would write A0, A1, A2, A3, and so on. It doesn't really matter. Just pay attention to what you're dealing with, the theorems that you're dealing with. We need things in the correct form to use, the definitions, the formulas, the theorems, so just pay attention to that, but it's not the biggest deal where you start everything. So something you could try to do for yourself is, okay, let's say I want the same sequence, this one here, but I want to start instead A0, A1, A2, A3. Rewrite the closed formula that we have here, now starting with n equals 0, because it's not exactly the same thing. So that's a fun thing you can try to do if you prefer to start at 0 when you're counting these. Okay, so the way we define sequences, we've already seen a little bit of this. So we've just saw an explicit formula for a sequence. We saw these where we might just write the terms out, and if we do it this way, then whatever pattern you start to see is the implied pattern. There are other ways to do this. Recursive formulas is the first piece here, but we're not going to do that in this class. So we don't need this. This is a fun example, which I may do a video for if you're interested in kind of checking it out, but again, is not necessary. So don't worry about the fun example. Get rid of that. So we're really just going to be focusing on, here's a list of numbers with a pattern, and can you make an explicit formula out of these things? So for example, this one, you can just do some of the terms. A1 would be 1 over 2. A2 would end up being 2 over 3. A3, 3 over 4. And you can keep going. Okay, so let's keep working. All right, so visualizing now these is beneficial. We're not going to really get into it as much. Again, this is just extra, so you do not need this. But if you're interested in kind of playing around, digging a little deeper, this is a pretty interesting YouTube video. But one way we can use a visualization is to answer this question, which is important. So what is the long-term behavior of our sequence? So this is the same as when you learned it with functions. When I used to ask that, I'm asking, okay, in the long run, as you plug in bigger and bigger values, what does the function do? I'm asking the same thing here. What does the sequence do in the long run as I plug in really, really big numbers? So we could attack this question a few different ways. We could look at a table of values where I do, here's n, here's a sub n, and I'm plugging in things like 100, 1,000, 10,000, and so on. And I'm trying to figure out, okay, do I see a pattern here? So we've played around with that a little bit already. You've done that in some Mathematica stuff you played with, so it's not too bad to do that, and I'll show you a Mathematica file with that in just a second. So what we're trying to get through here is what happens as my input gets really, really big. You've already actually answered a question like that, and the question you've answered that's like that is a limit. So we're interested in, here's a sequence, can I get an equation for it, a closed form, explicit formula, and then what happens eventually? Can I figure out what the limit is? All right, and that's just the long-term behavior. Does the sequence of numbers get bigger and bigger and bigger all the way to infinity? Does it go to negative infinity? Does it not have some point it's trying to get to? Is it just bouncing around forever? Or does it actually have a limit and get closer and closer to some number L? So let's actually just dig into a couple sequences in Mathematica right now to see some of this. So I have this will be on Blackboard, you can play around with this, a couple different sequences. So I'm just going to define a few of them. So let's see, 1 over n, and the definition is not bad, you just do it like a function, shift enter, 1 over n cubed, we can plug that in, and that's not too bad either, oops, shift enter, let's do one more, well, let's do e to the n, this one will be a little different, so let's plug those in. Okay, so again, like I said right at the beginning, we can make values. So we can do a table of values here. So I already have the code set up here to do a table, right? So what I've done here is I've just looked at the two sequences, 1 over n and 1 over n cubed, plugging in from 1 to 10. So then my question becomes, what does this do in the long run? What happens when I plug in really big numbers? So you could just try to think through this, but you can also start plugging in really big things. So we could go 1 to 1,000, and we can go by 100. So let's try doing this new table. Okay, and we see what's happening here. So a sub n, which is just 1 over n, starts at 1, and then gets pretty small, and then continues to get smaller and smaller as I go down the list. Okay, so then b sub n now starts at 1, and then immediately, that's 10 to the negative 7. That gets really small very quick. And as we go down this list, it's getting smaller and smaller and smaller and smaller. So just from this table, you might want to think to yourself for a second, okay, what's happening here? What's this long run behavior I'm seeing? So a sub n, which is 1 over n, When I look at that in the table, that looks like that's approaching 0. So how would I write that? I'd say the limit as n goes to infinity of a sub n or 1 over n is 0. Have I proved that to you? No, but this is just looking at the table, trying to get the idea. It looks like the same thing is happening with b sub n, which is 1 over n cubed. It looks like that one, as I take the limit of this, and again I can write this as b sub n or 1 over n cubed, looks like that also goes to 0. And we have a little experience with this. I'm cubing the bottom here, so then when I plug in bigger numbers, I'm going to get to 0 quicker than 1 over n. So we've actually played around with this a little bit before when we were doing integration and we were integrating all the way to infinity. And some of that intuition you've already built up from that is going to be really helpful here. Okay, so we could do something similar with en. So let's do that. Let's add in e sub n in here, and we'll add in a little column for that. E sub n, just like to see something a little bit different. So click, 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 click. Okay, so e sub n, this is 3/2 all raised to the n. So let me write that in here. E sub n, oh, I covered it up, whoopsie. So e sub n, let me move this over, is equal to 3/2 to the n. And our question is, what in the world is happening to e sub n as n gets really big? So let's bring this back over. As n gets bigger and bigger and bigger, it starts at 1.5, and then immediately when we plug in 101, we get to 10 to the 17th. That's huge. And as you go down this list, it's bigger, 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 bigger. So the question is, well, what is that approaching? That looks to be approaching infinity. Okay, so then just like integrals, we have words for this, and they're the same words and the same ideas. If this limit exists and equals some number, this case and this case, we call these convergent, or the sequence converges. If we're in this scenario where we go to infinity, we call this one divergent, or say that the sequence diverges. So it's just like what we did with the integration. You actually, in the previous one, you do the integral, you get to a limit, you evaluate the limit, see what happens. Here, what we're doing is a little different. We have this limit just set up for us, and we just have to evaluate it. So same idea as before, super similar, which is pretty nice. So what we can do is we can just calculate a bunch of different limits for all these different sequences and see what happens. So that's what we're going to do, but we need to build some tools to be able to do that. So before we go on to this is again for fun, but we don't need it, so don't worry about that. So when we're doing these limits, so far what do we have? We have the limit as n goes to infinity of some sequence a sub n. And I'm asking the question, does this equal L? Okay, so we have a ton of tools from Calc 1 when we are in this scenario. I have the limit of a function f of x, where x here, x comes from, so this is inside, that's this symbol here, the real numbers. So x comes from the real numbers. So if I have some function where its inputs are the real numbers, not just natural numbers, but real numbers, then I can talk about this limit, and I have a ton of ways I can do that. So right now you should just think to yourself, how do I do limits? Do I have any tools for doing limits? And so we have some basic ones. So what do I know about limits from Calc 1? What do I know? I got the basic ones, which we've already kind of talked about. I know limits that involve e. I know some natural log limits. I know limits that involve 1 over x. I know some of those, or 1 over x to the p, where p is bigger than 0. I know some of those limits. I got some other rules. So L'Hopital's, I remember that rule. That's really good. I know tricks with rational functions, where I could just compare the highest power of the numerator and denominator and say what's going to happen. So all of these tools that you built from Calc 1 are super valuable, and we're going to use them. But here's the thing. We don't actually have this scenario. We don't have a function on the reals to use these rules. So the way that we do this is we convert from a sequence to a function. All right? And I know this is a little bit of a weird idea, and in general, it's actually really, really simple to do. So let's just start with a quick example. So let's take the sequence, which you've already looked at, 1 over n. Okay, now I need a function such that whenever I plug in one of these n, remember n is 1, 2, 3, I need a function that will be the same value at every one of these n values. So I need some f of x that looks like this function whenever I plug in 1, 2, 3, whatever. So you should think about this for a second, but you shouldn't think too hard, because you should just pick whatever should be the most obvious thing, which is just the function itself. So 1 over x and 1 over n are going to match whenever I plug in one of these n values. So if you were to actually graph these two things, right, then what you would get is, so let's do green for this one. So I would get 1 would be 1, and then at 2 I'd get 1/2, and at 3 I'd get this, 1/3, and then 1/4, and then 1/5, and so on. Now, if instead I looked at this function, well, it would still hit all of these points. It would just also hit everything in between. So that function would look like this, all the way through. So the idea of this is, if I can find a function, f of x, that matches my sequence, whatever sequence I give you, if you can tell me a function that matches that sequence, then anything you learned about doing limits for this, you can then apply to this. And that includes all of these limit ideas from Calc 1. So if you have to use L'Hopital's, if you have to just say, oh, this is a function I know, 1 over x, I know that goes to 0, that implies that this sequence will go to 0. So you can use all of those tools, but you first need to find a function that fits your sequence. They have to match here for every single value of n that you could plug in. No, I'm not going to make you show that that's true, because it's the obvious choice in every choice I'm going to give you. So you don't have to prove that these two functions you get here and here match each other, but you do have to be able to just make that step. All right, so just to kind of write this out, the theorem that we're going to be using is if the limit of f of x, so this is some function that we're used to, Calc 1, pre-calc, regular old functions, if the limit of this function equals L, as x goes to infinity, and the function and your sequence match, so this is your function and your sequence match each other for any of these n's that we're going to plug in, then knowing this and the functions match each other, we can say that actually the limit of my sequence is the same as the limit of the function. So this is a very wordy way to say, if I know that I've got some function here that matches my sequence, let me just do a limit of a function because I know how to do that better, and I know that that will work for my sequence. So that's the theorem. Pretty nice. Just convert to a function, do a limit, because you know how to do those limits. Okay, so what does that mean in terms of actually using some of these? So here's an example. We have the limit of the function 1 over x to the r, where r is just some number. All right, so we know about these functions. So what you should be thinking to yourself right now is like, well, what do I know about 1 over x to the r, where r is a number? Well, we could try a couple of these. If r is 1, then this is 1 over x. I know about that function. If r is 2, well, I know about this. I know about 1 over x squared. That's, that's not too bad. I can deal with that. I know about r equals 1/2. This is 1 over x to the 1/2. I know about that function. I know about, what about -1? When r is -1, this is 1 over x to the -1, which is x. So, okay, I know about that function too. All right. So what I want to say is, okay, well, what are the limits of these things? So let's just go through the list. The limit of 1 over x as x goes to infinity, this thing goes to 0. This one goes to 0. Okay, this one well, that goes to 0 still. What's this one do? This one goes to infinity. Okay, what about r equals -2? Well, that would just be 1 over x to the -2, which is x squared. That also goes to infinity. And so just from our Calc 1 knowledge, we can say that we know what this is. It's either infinity or it's 0. It's going to be infinity when r is less than 0, and it's going to be 0 when r was greater than 0. Now, we're missing one key thing here. What happens when r is equal to 0? Well, that's 1 over x to the 0, which is 1. Okay, what does that do as x goes to infinity? What's 1 do? Well, it's always just 1. That one's kind of boring. So we could also plug in 1 when r is equal to 0. But we're really not going to deal with cases like that. We're always going to stick with the interesting thing, but it's just for completion. Okay, so what does that tell us? Well, that tells us if I ever have a sequence that looks like 1 over n to the r, then I don't have to do any work because this function will match this sequence on anything I could plug in, and so I immediately can write this down. I don't even have to think about it. I know what these sequences will do because these two things match, so then these two have to match. And look at that. I've just gotten a ton of long-run behavior information for sequences. A whole bunch of sequences. I just immediately know what they do in the long run, which is going to be really, really useful for us. All right, so let's keep going. Okay, so here's a slightly different example. What happens to this sequence as n gets really, really big? So here's what people want to do. I'm going to just do it. Natural log of n over n. Let me just plug it in. Okay, natural log of infinity. I'm going to put quotes around all this because I can't really do this. Okay. Well, as I plug bigger and bigger things into natural log, I know that that gets really, really big. So what this does is this looks kind of like infinity over infinity, which means nothing to me. Although it should put a little light bulb up and say, oh yeah, L'Hopital's rule. Infinity over infinity is L'Hopital's. But again, that rule does not make any sense if my functions only take in 1, 2, 3, 4, ... Because remember, L'Hopital's rule deals with derivatives. Derivatives don't make any sense when all you're doing is plugging in these discrete numbers, 1, 2, 3, 4. So what we have to do is make a conversion first to functions we do understand L'Hopital's rule for. And again, it's just as simple as plug in x's, because we just want to convert to our inputs being real numbers. Now, again, we still get infinity over infinity, so then we can use L'Hopital's rule and write this as the limit as x goes to infinity of, now take the derivative of natural log, that's 1 over x. The derivative of x is 1, so that's the limit as x goes to infinity of 1 over x, which we just know, and again, you can just use this as a fact. If you don't remember it, you've got calculators, you can do your, well, what's 1 over x look like? It looks like this. Oh, hey, I'm going to infinity, so that's 0. And there you go. So altogether, that means that the limit of a sub n as n goes to infinity is 0. Now, what's your intuition on this? Think about the two pieces you have here, right? Natural log goes to infinity, which we just looked at, but it does it very slowly. And so that's the piece you're looking at, is you're just trying to compare which of these things is faster. And here, the bottom's faster, so that's going to drag everything down to 0. All right? Okay. So, we've got many Calc 1 limit rules that are just nice to remember. So a lot of these are what you know from derivatives and integrals and things like that, so that's really nice. We've got our addition rule, subtraction, scalar multiplication, the limit of a constant's a constant. Now we have to be a little careful here because this is not true for derivatives or integrals, but we have the limit of a product is the product of limits if we have convergence of individual sequences. Be careful there. We can split up division into division of limits, again, only if each of these is convergent itself. So this does not work trying to do infinity over infinity stuff, because those aren't convergent. Another really nice idea is if the limit of just a sub n itself is convergent, goes to something, then if I have a power in here, I can sneak the limit inside the power. And there's a couple extra conditions in here, that the power has to be positive, and so does each element of the sequence. So every single a sub n has to also be positive. But some nice limit laws. So just try to remember these. They'll come in handy as you do limits in the future. Okay, so then the next really nice limit law, and this is important to understand because we have other theorems that are going to be very similar in ideas to this, that are going to help us a lot with doing series tests later. So the squeeze theorem is a theorem that tells you how to figure out the limit of a sequence in a specific situation. So what's the situation? Well, I've got three sequences, A, B, and C here. If I somehow know, and the somehow I know is going to be, I'm going to pick these two to be as easy and straightforward as possible. So what's the setup to the squeeze theorem? You've got some sequence B sub n. So you're going to start with some sequence B sub n here that you don't know about. What you're going to do is go, do I know about any sequences A and C that can squeeze B? So the way that I like to think about this is B is a car on the highway. So right here, if there's a big truck A and another big truck C that are squeezing this car, and both the big trucks want to get off the exit. Well, if you're car number B, or your letter B, then if these trucks are squeezing you and there's no way to go above or below any of them, that's what this is saying, is that B is never going to break out of A or C, just like this car is never going to be able to get past B or C, or A or C, sorry. If A and C both want to get off the exit, then this little car that's stuck between them also has to get off the exit. So the squeeze theorem says if I have two sequences that both want to do something, then you know that the sequence in between them also has to do that thing, which is very clear based on this picture of two bears hugging. So obviously the bears hugging is what you need to remember from all this. So there's the statement of the theorem. Pretty nice thing. If I can take my B sub n, I can stick it in between two other sequences that go to the same L, so they both have to converge to the same L here, then my initial one, no matter how complicated it looks, my initial sequence will get stuck in between those and also converge to that. Super, super useful idea. Really, really helpful for us, and something that we're going to want to go to, and things like this in the future we're going to want to use. Okay, so let's use an example. So we're just going to do this first one. The second one is a little harder, but is something that we can think about later. So squeeze theorem. Okay, so I'm going to change one thing in here just to kind of stick with the way we were thinking of these things before. Let's let B sub n be sine of n over n. So I know some of you are sitting here right now going, oh no, trig, why, Gary, why? You're going to find that actually trig is really nice in these types of problems, and you'll see why. So what was the goal of the squeeze theorem? I need to take my B sub n, and I've got to squeeze it in between two other sequences. Now these sequences can be anything you want as long as the A sub n is smaller and the C sub n is bigger. Okay, so I look at B sub n and I say, well, I got the bottom here, right, this little n, and I know what this is going to do. As n gets really big, this is going to get big. but there's no clear way for me to kind of put something bigger and smaller than that that I think will be very helpful. So then I look at the top and go, what do I know about sine? So I think to myself about sine, what do I know about this? And you could even do a little drawing for yourself. Here's sine. And what you should notice and think about is I'm squeezing, squeeze theorem. So I need something above and below. So what I can do that pretty easy. Here's something above. Here's something below. I know sine is always between 1 and -1. Okay, so I'm just going to write that down. Here's -1. Here's 1. All right, and here is sine. So make sure you take a minute and believe that. Okay, so if I believe that I've done that bounding, that's really good. Then the next thing I have to think of is, well, I don't have my b sub n. I'm missing something, right? Over n. Okay, but what I've really just done is divided everything by n. And n is positive, so that doesn't mess up flipping anything. And there we go. I've taken my b sub n and I've bounded it by 1 over n and -1 over n. So then, well, what did the theorem say? Let's go back for a second. The theorem said, if I can do this bounding below and above, awesome, and I can show that my sequence below and above both converge to the same number, then my middle sequence, the one I started with, the one I care about, has to converge. So let's look. What do these converge to? Okay, well, just off to the side here, the limit as n goes to infinity of 1 over n. Do we know anything about this? Well, we just actually played around with this, right? We said we had a formula for this. 1 over n was going to go to 0. And we actually saw this in the Mathematica as well. And then, well, what about this one? -1 over n. Well, if I go back to my rules, I know I can take a constant out. So let's do that. Negative limit n goes to infinity of 1 over n. And oh wait, you just told me that the limit of 1 over n is 0. So, okay, this is -0, which is 0. So I did it. This goes to 0, this goes to 0. So then by the squeeze theorem, sine of n over n must go to 0. Therefore, it is convergent. Ta-da! I did it. So this one's tougher. If you want to try to bite off something a little bit more difficult, you can try this. And there's also a definition in here that we are going to use later called the factorial. So if you're not sure about this, if you've never seen this before, look up factorial. I'll give you an introduction on it a little bit later, but we are going to use it. All right. So there's a couple other theorems that are useful for us to use in here. So I'll start with this one actually on the bottom. If the absolute value of a sequence goes to 0, then so does the original sequence. This is pretty useful. An example that's not too bad. The limit as n goes to infinity of -1 over n squared. Okay. So what does this do? Well, I've got two ways to do this. Either I can take out a negative, which is 1 over n squared, and then I can just deal with this limit without the negative. Or I can say, well, I know what this is. The absolute value of -1 over n squared is just 1 over n squared. And I know that the limit as n goes to infinity of 1 over n squared, well, that's 0. We have a previous result that says 1 over n to the r will be 0, that limit, as long as r is positive and 2 is positive. So by this theorem, right above, since the absolute value of a sub n will go to 0, then that means this original one, right here, also goes to 0. Done. All right, so this one at the top is a little bit tougher. If f of x is continuous at L and a sub n goes to L, then f of a sub n goes to f of L. So let's think a little bit about this. So I have some sequence, a sub n, and it goes to L. Then I know then that when I apply a function to my sequence, I know what will happen there. So we actually don't usually use it in this order. We usually have a situation like this, and we want to know, well, what happens here? And what this is telling us is that under the condition that this function f of x is continuous at L, I can just, instead of answering this question, I can just say, well, what does this do? And then apply the function afterwards. So, let's just try something not too bad here. So let's say I want to know what happens to, let's think, let's not do that example. How about, something like a sub n is 1 over n. All right, so then I know that the limit as n goes to infinity of 1 over n, well, that's equal to 0. So then if I apply any function that's continuous at 0, I know what the limit of that sequence is going to be. So think any function you want. How about the square root? So then what's going to happen to this? Well, by the theorem, this is just going to be the square root of this limit, which is the square root of 0, which is 0. Done. So this lets me, if I have a function of something, it lets me zoom into the something, do that limit, and then just let the function act on whatever answer I get. So pretty useful thing. It's just a way for us, once we get a limit set up, to go, this is too much stuff to deal with. Can I kind of start in the middle and work my way backwards? And what this theorem says is, yes, under certain conditions, you can just go inside and work backwards. So another way to think about this is, we did examples earlier where we had things like e to the negative n squared. Or we could do even something like, we could do something like e to the negative 1 over n. Oh, I lost my color. Okay, so if I wanted to know this limit, this kind of looks like a doozy, right? But I could think of this as e is the function f, and I'm doing it to a sub n here, where a sub n is just negative 1 over n. Well, do I know this limit? We actually said that was already 0. So then the limit of this should just be equal to e to the answer I got right here, which is 1. Boom. So a very important type of sequence is called the geometric sequence. This sequence is something you're actually already really familiar with. This form is a little weird. I know there's a lot of parameters. There's this a, there's this r. But if you just think about what's happening here, it's not too bad, and you've already seen a lot of this before. So the sequence starts off with a, so it starts with the value a, hint, hint. Then I multiply by r, and then I multiply by r, and then I multiply by r, and I keep going. This should scream to you exponential growth and decay. Okay, so following along that idea, this will be your initial value. So initial population, initial amount of money in the bank, whatever you want to think about. And then this r here will be your growth or decay factor. So then if you've studied these types of things before with populations, whatever it is, you know what's going to happen in the long run with this. So in the long run of the two interesting cases, I'll talk about that in just a second, what's going to happen here? Well, I'm either going to blow up forever, and that's going to happen when I'm actually growing. So that's my growth factor is bigger than 1. I'm growing each time. Or I'm going to go down to 0, and that's when my growth factor is less than 1 because I'm decaying. I'm taking away. Each step I'm taking away. Now, when my growth factor is equal to 1, in this formula, I'm just not doing anything. It's just going to be a forever. And we don't really care about that situation. because that would just turn into, so the situation I don't care about, a sub n equals a times 1 to the n minus 1. Well, that's just a sub n equals a, and that's just a constant, so we don't care because we've already covered that example. It doesn't matter to us. So for a geometric sequence, we're just going to say, let's make sure r is not 1, so we can deal with this. And the other point here that we'll talk about is, for right now, we'll just let a be positive for when we're thinking about this as a sequence. So there you go. I mean, geometry is not too bad. You can go into Mathematica and play around with this a little bit if you want to try to convince yourself. So as an example, we actually did a geometric already. So this one right here, e sub n, was a geometric. 3/2, that's bigger than 1, and it blew up. We could change this to 1/2 to see what's going to happen. So let's just make this 1/2 instead. Let's rerun the sequence. And it starts at 1/2 and then gets extremely small, extremely fast. So there you go. Something you can kind of try to play around with on your own if you want. So let me just fix that e sub n. I'm not going to make you do any of the visualization stuff, but if you're interested, you can do this discrete plot and you can look at the pictures of these things. It's not something that's really a huge deal for us to deal with. A couple other little things you could do in Mathematica. If you're not sure what's going on with these sequences, Mathematica can do the limits for you, which is super nice. So something else you can play with if you're really interested, but totally not important, off the highway, not important, there are really interesting sequences defined recursively that do really, really cool things. And so I'm happy to talk with any of you about any of these. You could just run this code that I have here, and you can check out some of these sequences that I've defined, but again, not important to get through the class, so don't worry about it. So I will post the worksheets and solutions to those. You'll still have your homework to work on. I will be, you may have already seen the video and description and email I'll send out about how we're doing the class. But just make sure you go look at that so you know kind of what's happening. I'm trying to make the class as similar to what we're used to. Same homework, same things. The Mathematica projects will be more straightforward in terms of what I'm asking and a lot less you doing Mathematica. So right now Mathematica will just become a tool you can play with if you want, but it's not going to be as much of a focus in the course. So make sure you're asking me questions. Make sure you're visiting my Zoom office hours, and I will see you in the next video.